Our last tutorial covered placing 3D objects onto 2D user interface widgets. Let's continue that work by focusing on optimization. First, let's address a major issue. Our previous 3D shape was rendering full screen, resulting in unnecessary and significant overdraw. To fix this, we must calculate the precise screen space bounding box for the object. This tutorial is based on the previous one, link in the description. You can do things following the previous and current tutorial. Or you can download the project from GitHub while watching this video for an explanation of the different aspects of the project. To begin, we'll determine the object's world space bounds, for example, by sampling 8 key points of the sphere. We then need to project these points onto the screen. This projection is achieved using the Model View Projection (MVP) matrix. In the previous 3D on Widget video, we discussed it. The tutorial becomes more interesting when something moves on the screen. Let's make a simple dynamic scene. Let's create a static sphere and a dynamic sphere with physics enabled. The dynamic sphere will fall onto the static one, roll off it, and move in some direction. I decided to mark object we want to track with specific tag, target. Now our target tagged sphere must be tracked by our widget. First we create a weak pointer to our target object. Since this object might be destroyed during gameplay, we are storing a weak object pointer. And as soon as the object is deleted, the pointer will automatically be invalidated. And before dereferencing the object, we will check its validity. On widget construction we iterate through all the actors with a tag for target. And store the pointer to the first one if they exist. After we have verified that the pointer is valid, we need to extract the object's transform. To obtain the correct final matrix, we must obtain the inverse matrix of the model. We can do this in 2 ways. First, take the matrix of the transform and invert the matrix. Or, invert the transform, then extract the direct matrix. Matrix inversion is a computationally expensive operation, much more difficult than transform inversion. We could rule out the inverse matrix option, but for non-uniform scale, the inverse transform will be incorrect, and therefore the matrix will be distorted. Matrix inversion is a costly operation, but it will not be noticeable for a small number of objects, so let's use it, since the result of its inversion will give us the correct object shape. As mentioned in a previous video, a big ray origin offset from this shape causes this dissolve artifact. We can fix it by placing it inside a distance-agnostic shape, like a bounding box. When the ray hits the box, the new origin will be placed at the hit position, and the distance to our cube sphere will always be small. But our widget is still full screen. Let's start placing it correctly on the screen. First, we need a canvas panel. Our image will be placed on it. We'll add the canvas panel in the header file and include the necessary canvas-related headers in the C++ file. Here, we must check if the canvas is valid. It will be invalid if there's no binding in the widget blueprint. We also check if our image is a slot, child, of this canvas panel. Once these checks are in place, we can move and scale the image on the canvas. Now, launching the game, we face a problem. Our blueprint widget compilation failed. To fix this, we must create a canvas with the exact same name as in our header. We'll wrap our image with a canvas and name it mCanvasRoot. Compile, launch the game, and we now see it placed where we intended in the code. In the code below, we used a transformation from screen coordinates to project rays into model space. But to place the widget on the screen, we need to do the opposite. Convert the model space coordinates into screen space. To do this, we will use the direct model view projection matrix, which is the inverse matrix that we are now calculating. Let's rework the code below. First, we'll calculate the model view projection matrix. We'll use it to place the widget on the screen. And we'll use the inverse matrix to convert screen space UV to model space rays. Let's first try to place a widget on the screen in the same position as we see the object. To do this, we multiply our matrix with the model's local position vector, which is 0 in our case, the middle of the sphere. If the W component is below 0, the object is behind the camera, so we exit the function because there's no reason to continue. Then, we calculate the normalized position from 0 to 1, and, by multiplying it by the canvas size, we get the coordinates of the widget on this canvas. We'll set the widget size to 200 for now, we'll calculate the correct size later. To see the widget, we temporarily set a solid semi-transparent color inside the shader. You can attach any widget position to an actor or world space point this way. Let's project the object's bounding box vertices onto the screen, and then calculate their screen space bounding box. As our object is 100 cm radius, we will make 100 cm extend bounds. Initialize our model space bounds. Initialize screen space bounds with minimum 1 and maximum -1 in the beginning. The screen bound size, we calculate later, is maximum minus minimum. In initial case, the size is -1 equals -2. If the x or y size component is negative, we exit a function and make the widget invisible. It can happen when the minimum and maximum values are not updated within this loop, due to w component of each projected point is negative. Next, the minimum and maximum will be clamped in the range of -1 to 1. Therefore, if both the minimum and maximum are outside the screen bound on the left, for example, both x components will be clamped to -1, and the widget's width will be 0, causing the function exit at this point. Then we normalize the coordinates to the canvas, and set the widget's position and size. Let's look at the result. We can use a draw debug points to double-check the bound vertices. Let's update our shader to make the shape visible as well. Add saturate function, it is clamped from 0 to 1 in HLSL. And add 0.3, so the opacity will be set in a range from 0.3 to 1.3, clamped to 1. Let's look at the result. This technique is the exact mechanism I use to calculate the position and scale for both the ghost and the force overlay widget in the game. The slightly visible frame you see is the bounds of the ghost widget. The same frame you can see in force overlay widget. I initially created this frame for debug purposes, but I decided to leave it as is. At this point, the goal of our tutorial is achieved. I have uploaded all the code to GitHub. It is based on Unreal 5.5. You can see a visually modified version there. Also, there is a game-related ShaderToy repository. Feel free to check it out. Please like, subscribe, and if you want to support a Tsuka Race development, you can buy it on Steam. Thank you for watching.